Our multiplication rules for probability. Basically, the multiplication rules are used when we're going to find the probability of more than one event happening. So previously with our addition rules, we might have selected one person at random or one card out of a deck of cards, might have rolled a single die one time, something like that. So with our addition rules, we were find the probability of a single event happening. Multiplication rules, we might select three people and find out whether they could do this. Or we might pull out 5 cards from a deck of cards and find out which ones are which. So our probability of several events happening in succession would be our multiplication rules. And those multiplication rules are based on one basic idea, whether or not events are independent. Oops, let's try that again. Independent or dependent. So if two events are dependent, that means the outcome of one affects the outcome of the next event. We'll use our deck of cards as an example. Let's say I'm going to pull 2 cards out of a deck of cards, and I want to find the probability of the first one being a king and the second one being a king. If those events are dependent, that means the cards are not replaced after each draw. So the probability of getting a king the first time is 4 out of 52. There's 4 kings in a deck of cards, 52 total cards. Now, in order to move on, one of those first 2 cards had to be a king. So we pulled out a king. There's only 3 kings that are left. We didn't put it back in, so there's 51 total cards that are left. So notice the outcome of the second event was dependent on what happened with the first event, hence the name dependent events. Now, again, one more time, 4 out of 52 is how many kings are in a deck of cards, 4, 52 total cards. Since a dependent event, we did not replace that card, so to move on to the second event, it had to be a king. There's only 3 kings left, 51 total cards left. If those 2 events were independent, then our cards would be replaced. So our probability of drawing a king, it'd be 4 out of 52. Once we drew that card, we put it back in, so there's still 4 kings left and 52 total cards. So our probability from one event to the next does not change, whereas dependent events, it does change. So with that being said, our rule is written right down here. For dependent events, the probability of A and B occurring, so probability of a king and then another king, is the probability of a king times the probability of another king, assuming the first king has already been drawn out. So making that point right there, that little slash sign there is not a division sign. It means this last part right here, I'm just going to write this out, the probability of B assuming that A has occurred. So the probability of the second king assuming the first king has already been drawn out. Okay, so 2 events are independent if the probability of the first and second events are related to each other. Okay, so right here it spells it out. Dependent events are events where the probability of one event is affected by the probability of the previous event. And our deck of cards probably gives us the best illustration of that. Also noting, I guess, here that back in our addition rules, we added our probabilities together and notice that we are multiplying these 2 probabilities together. Okay, a probability of A times a probability of B, assuming that A has occurred. If our 2 events are independent, so the probability from one event doesn't affect the probability of the next one, then it's simply the probability of A times the probability of B. So probability of a king times the probability of a king gives us our probability of both king and a king. A couple of offshoots of that. If we have a probability of at least one event occurring, so let's say we're going to draw 3 cards out of a deck of cards, we want to find the probability of at least one king. We'd have to find the probability of 1 king, add that to the probability of 2 kings, and add that to the probability of 3 kings. So we've been going through that process for 3 cards 3 different times. So a little bit of a shortcut is find the probability, in this case, of no kings, which is essentially the opposite of at least 3, and then subtract that from 1. So that's the idea of the complement we talked about back in the first section or two, that no kings is the complement of the event of at least 3. or at least one, sorry, at least one. So a shortcut is just do that probability one time and subtract it from 1. And you can see that pictured here. The probability of at least 1 is 1 minus the probability of none. I'm going to rephrase this word none as being the opposite of the at least 1. So when I say at least 1 king, the probability of no kings. Okay, so that method. And then especially when events happen in a sequential order, a tree diagram might help. So if we were to flip a coin, say 5 times, and we want to find the probability of exactly 3 heads, my tree diagram might help us out by going heads and tails for each of our 5 coins here, all the way across, all the way out 5 times, and then running out our sample space and using that to come up with our probability. So a tree diagram will be helpful. It basically, I'm going to say it's probably used in two key areas. Number one, when we have events that happen in a sequential order, as I already talked about, or you might even use a tree diagram when you simply have to sort information out because there's so many different paths that you can take here. So a tree diagram can be useful to help sort information out. Oh, so let's look at how our multiplication rules are applied. You can see our first example says 3 cards are drawn from an ordinary deck of cards and not replaced. So here's our key statement. Not replaced makes those events dependent. Find the probability of getting 3 jacks. So the probability of a first card being a jack is 4 out of 52. There's 4 jacks in a deck of cards, 52 total cards. Okay, to move on to the next event, the first card had to be a jack, which means there are 3 jacks left because we're not replacing it, and 51 total cards. And one more time, we now put out a jack here and a jack here, so there's 2 jacks left and 50 total cards here. Now, those fractions could all be simplified. When I wrote them down, I wanted to see the 52, 51, and 50, so we could illustrate that. But 4 52nds is 1/13th, 3 51st is 1/17th, and 2 50ths is 1/25th. And our probability then is 1 out of 5,525. Okay, starting over letter B, getting an ace, a king, and a queen in order. So the probability of an ace is 4 out of 52. We pull out an ace, so move on to the next event. The next event is a king. Well, there are 4 kings in a deck of cards, but we pulled out one of those aces, so there's only 51 total cards left. And then our third card being a queen, there's 4 queens in a deck of cards, but we pulled out an ace and a king. There's only 50 total cards that are left. So here you can see, once again, the same idea. We could simplify these down. 1/52nd, or 4 52nds is 1/13th. The 4 out of 51 is not going to simplify, but the 4 50ths will simplify to be 2 25ths. And if we multiply that, we get 8 out of 16,575. All right, dependent events. Zipping through 2 more of those, a club, a spade, and a heart in order. The probability of a club, there are 13 clubs in a deck of cards, 52 total cards. We've now pulled out a club. Move on to the spades. There's 13 spades in the deck of cards, but because we pulled out 1 club, there's 51 cards left. And then we move on to our heart. Again, there are 13 hearts in a deck of cards. We pulled out a club and a spade, so there are 50 total cards that are left. Let's go simplified here, 1/4 first. 13 out of 51. Oops. Yeah, 13 out of 51 is going to stay as 13 out of 51. And then 13 out of 50 will also stay. So we get 169 out of 10,200. One more time with our deck of cards, all 3 of those being clubs. 13 clubs out of 52 total cards. We pull out a club, so there's 12 left, 51 total cards, and then there are 11 left out of 50. We'll go a little different path here. I'm going to cancel, so I have a 1 and a 4. This will go with a 4 here, so I'll cancel that out. 12 and 4 can both be divided by 4. 4 divided by 4 is 1. 12 divided by 4 is 3. I'm going to go a step further there, then 3 and 51 could be on a 1 and a 17. And then I can multiply straight across. 1 times 1 times 11 is 11, and 50 times 17 is 850. So 11 out of 850 is our probability here. Okay, so our first look, our first 4 problems were dependent events. Moving on here, 17% of the people in the United States smoke. Find the probability of picking 3 people at random and finding that all 3 smoke. I'm going to go a little bit different route here. I'm going to show us 3 blanks. We're going to pick 3 people at random. The probability the first person smokes is 17%, or 0.17, times. Now our percents, if I select one person here and one person there, that percent doesn't change from one person to the next. The probability the second person smokes is also 17%, which means the probability the third person smokes is also 17%. Once again, those percentages from one individual to the next don't change. That's the same thing as 0.17 to the third power, and that winds up being 0.004913. Okay, so basically the bottom line here is our percentages do not change from one event to the next, which should make the next problem a little bit easier. 44% of the professors at a 4-year college are female. If you sign up for 5 classes, find the probability that you get all female professors. So we have 0.44 times itself 5 times for all 5 professors. I'll go ahead and write out that long version. That's the same thing as 0.44 to the 5th power, or the chance of having all female professors is 0.0165. Now some people might write that as 1.65%. Okay, we've already talked about the fact that our probability can be a decimal, a percent, or a fraction. Any one of the 3 is acceptable. Here I have 2 of the 3, the decimal and the percent. Oh, let's keep moving on here. Back here at the top, a box of 35 computer components has 6 that are defective. You test 2 of these components, so testing 2 separate components, find the probability that both work properly. Okay, so the first thing to note, if 6 are defective of the 35, that means that 29 work properly. So probably the first one we select works properly is 29 out of the 35. From here, like I just said, we're not going to select the same computer component twice. We're selecting 2 different ones. So we already selected one that works, which means there are 28 left that work and 34 total. I'll go the long route here to begin with, and then maybe show you a shortcut if we haven't already seen it. But 28 and 35 can both be divided by 7. So I'm going to divide those and get 4 and 5. And then 4 and 34 here can both be divided by 2. So I'll go with 2 and 17. If I multiply straight across, 29 times 2 is 58. 5 times 17 is 85, so 58 85ths. Let me go away from this here for just a second, because we can show you a little bit of a simplified, I don't know if it's a simplified version or not, but it will show us how we can simplify this with our calculator. So give this a minute to pull up, and we'll see how that fraction can be done on the calculator as well. There we go. Okay, so I'm going to clear here. And we had 29 divided by 35 times 28 divided by 34. Okay, so I just typed in my 2 fractions to multiply. I hit enter. It does give me my answer as a decimal. So as remember, our answer can be in a decimal, so we could write this down as 0.68235, whatever we wanted to write. Or our calculator will convert that to a fraction underneath the math function. Number 1 is a fraction, so I'm just going to click on or hit enter on that, hit enter a second time, and notice there's my fraction of 28 85ths. Okay, so the graphing calculator can make life a little bit simpler as we type those fractions in if we want to keep working in fractions. Let's move on here. In a class of 30 students, 5 made A's on the first test. If 3 students are selected at random to do a special project, find the probability that all 3 students made A's on the first test. So notice we're selecting 3 different students, not the same student 3 times, but 3 different students. So the probability the first student we select made an A is 5 out of 30. We've now selected somebody who got an A on the first test, so there are 4 people that are left that made A's, 29 total people to choose from. And then we select one more, 3 people left that made A's, 28. And if we go ahead and multiply that, we can do some canceling. We get 1 out of 406. I'll leave the canceling to you or your calculator. Okay, a couple of kind of tricky ones here with the wording. 23% of the class passed the first and the second test. 45% of those that passed the first test also passed the second test. Find the percent that passed the first test. So what's being implied here, but probably not spelled out well enough, is the fact that you can't take the second test until you've passed the first test. So I'm going to write this long version first. Probably the first and the second test is the probability of passing the first test times the probability of passing the second test, assuming you've already passed the first test. So as I mentioned, you can't move on to this event until you've passed the first test. So we fill in the numbers. It tells us that 23% passed the first and the second test. Of those, 45% passed the first and the second test, so 45 here, which means we need to find out who passed or what percent of the class passed the first test. So here, I'm going to divide by 0.45 to get the first test by itself, and the probability of passing the first test is about 51% or 0.51. So kind of backtracking here, if we had 21 people take the test, what this means is of those 21, probably somewhere around 11 passed the first test. Okay, right here, 11 of the 21. That might be somewhere, probably a little bit high, but somewhere around 51%. Now, of those 11, maybe 5 of those passed the first or passed the second test. So that 5 out of 11 represents the 45%, and overall 5 out of 21 represents the 23%. Okay, so that's kind of backtracking on what that looks like. And that should make the next one look a little bit more straightforward. 35% of the adults in America eat a healthy breakfast. 18% of the adults eat a healthy breakfast and exercise regularly. Find the probability that a person who eats a healthy breakfast exercises regularly. So the probability of eating a healthy breakfast and exercising regularly is the probability of eating a healthy breakfast. Oops, let's try that again. Eating a healthy breakfast times the probability of exercising regularly, assuming that we did eat a healthy breakfast. So it says 35% eat a healthy breakfast, 35% here. 18% of the adults eat a healthy breakfast and exercise regularly, so 18% goes here. And we're trying to find the probability that they exercise regularly. So we'll divide by 0.35 to get the probability of exercising regularly by itself, and 0.18 divided by 0.35 again is about 0.51 or 51% eat a healthy breakfast and exercise regularly, or exercise regularly, assuming they have. Okay, so there's our multiplication rules. Let's go here to the top, look at a special situation or two. Evening weather report says there's a 30% chance of rain tomorrow. When it is raining, John takes the bus to work half the time and drives his car half the time. When it's not raining, John takes the bus 25% of the time and drives 75% of the time. What is the probability that John takes the bus tomorrow? Okay, so these are sequential events. When it rains, he does 2 things. When it doesn't rain, he does 2 other things. Okay, so to start out with, there's 2 things that can happen tomorrow. It can rain or it cannot rain. So we'll start those as our 2 branches. The chance of rain tomorrow is 30%. The chance of it not raining then is 70%. Now off of that, if it rains tomorrow, it says that John, when it is raining, John takes the bus to work half the time. So bus, he takes 50% of the time, which means he drives the other 50% of the time. If it's not raining, John takes the bus 25% of the time, and he drives then 75% of the time. And we want to find the probability that John takes the bus tomorrow. So I follow my branches out here. Rain and bus is 0.3 times 0.5 plus, when it doesn't rain, John takes the bus 25% of the time. So 0.7 times 0.25. And those numbers are 0.15 plus 0.175, or John's chance of taking the bus tomorrow is 0.325 or 32.5%. Okay, so our tree diagram helps us sort those options out. Again, a sequential order. Rains, then he does this. Doesn't rain, then he does this, with each percentage listed there. Our last special situation is that at least one idea we mentioned earlier. So 12 women and 8 men are called for jury duty. If a jury of 6 is selected, find the probability that there will be at least one woman on the jury. So the long version here, at least one means 1, 2, 3, 4, 5, or 6 women on the jury. Those would be at least one, a jury of 6. So we have to find the probability of 1 woman, of 2, of 3, of 4, of 5, and of 6. Add all those together, and then in this case, that could be quite a long process because of the fact we're selecting 6 jurors. So a shortcut version is 1 minus the probability of none, or in this case, I'm going to write no women on the jury. Okay, so at least woman, the opposite of that is no women on the jury. So 1 minus the probability of the first juror we select is not being a woman. We have 20 total people to choose from, 12 women and 8 men. Of those 20, 8 are not women, 8 are men. So 8/20ths are probably not getting a woman on the jury. We're not going to select the same man twice, so our next juror is 7 out of 19, 6 out of 18, 5 out of 17, 4 out of 16, 1, 2, 3, 4, 5, and we have one more juror, so 3 out of 15 as we go down, because we're not going to select the same juror twice in a row. Okay, 6 different people on the jury. We could do some canceling in here. Let's go here. Let's do the easy ones here. I have a 1 and a 4. I have a 1 and a 5. I have a 1 and a 3. I have a 2 and a 5, both being divided by 4. As we continue on, it looks like the 5s could also cancel here and here. What else? The 2 and the 4. So I could get the 2 and the 4 down to 1 and a 2. And I wind up with 1 minus 7 over 9690, which winds up being 9683 over 9690 as our probability. Maybe we should show the intermediate step there. 1 is 9690 over 9690. Something divided by itself is 1. Or dividing with fractions, we find a common denominator. So it goes from here to here to here. Hopefully that makes sense. Obviously, again, you could use your calculator to simplify that as well. There's the long version. One more time here. There are 26 inmates in a county jail, and 5 are in for violent crimes, which means 21 are not in for violent crimes. If 3 are picked at random for a work detail, 3, find the probability that at least 1 was in for a violent crime. So at least 1 would be 1, 2, and 3. In this case, probably not too awful long, but still 3 times as opposed to 1. So we're going to do 1 minus the probability. So at least 1 was in for a violent crime, so that none for violent crimes. Opposite statement there. Okay, so 1 minus the probability. First one not being in for a violent crime is 21 out of 26. Second one, we're going to select the same inmate twice, so it's 20 out of 25. And our third one not being in for a violent crime is going to be 19 out of 24. I'm going to do the same simplification I did up above. Cross-canceling any numerator at the end of the denominator. So I'm going to go here up and down. 20 and 25 can both be divided by 5, so I get a 4 and a 5. Oops. The 4 and the 24 can both be divided by 4, so I'm going to go down to a 1 and a 6. And the 21 and the 6 can both be divided by 3, so I'm going to go down to a 7 and a 2. And it looks like that's probably all the farther I can go. So I have 1 minus, and across the top, 7 times 19 is 133. 26 times 5 times 2 is 260. And 1 minus that, I'll go the long version, 260 over 260 minus 133 over 260 gets me 127 out of 260. So there is a look at our multiplication rules.